Hi, and welcome back to Geology. Now I'll continue on with the introduction to volcanoes, looking at more on basalt lava flows and then also some andesitic and rhyolitic lava flows. Columnar joints, right? So one of the key things about columnar jointing is that the joints are always perpendicular to the cooling surface, right? So in this case, the cooling surface for this lava flow, this is actually Devil's Post Pile over by Mammoth Lakes, California, in eastern Sierra Nevada. And so this lava flow, as it cooled against the ground surface, then up against the atmosphere, right? And you get these columns. And I'll depict how these form. Here, Devil's Tower in Wyoming is also heavily columnar jointed, and it's really a basaltic neck of a volcanic structure. It's a little strange to have these columnar joints of these necks, but let's look at back over here, and we'll kind of look at this columnar jointing. So one thing that happens with columnar jointing, it's a cooling feature, right? And one thing that we know is when we have something hot, and as it goes to solid and cold, there's going to be a contraction, right? So it's going to shrink. It has to shrink or contract. And so imagine we have some lava here, right? And as that lava cools, it's going to cool in a very natural geometric design. So imagine these being 120-degree angles, right? Each of these are 120 degrees all the way around. So if you add 123 times, you get to 360, right? A full circle. And so if I start cooling these 120 degree angles at each of these corners here, right? Each of these corners, what I start making a very, very unusual geometric shape here, right? Each of these are 120 degree angles. And so that geometric shape I'm going to start making this kind of honeycomb type structure, right? And this honeycomb type structure are the columnar jointing. And so usually it's 5 to 6 sided, sometimes 7 sided, but it's a very unique pattern in nature. And you probably see the same pattern occur in mud cracks, right? When there's a puddle, it dries up, you get these mud cracks. So it's a very unique pattern in nature. And then for pillow lavas, one of the things that happens with pillow lavas, remember, the first thing we can say about pillows, it's going to be a subaqueous eruption. In other words, the lava's underwater. Either a lava flow in Hawaii flowing off the volcano and entering the ocean, and that's going to be a minor one, but where it's going to be most common is at mid-oceanic ridges. In fact, the sea floor is covered by pillow basalt lava. And let's see what we have here. Yeah, so here's a pillow basalt. And so, in fact, here in coastal California, because much of the rocks we have here in the coast ranges are oceanic rocks, and there's sediment sitting on top of these fragments of ocean floor, and the ocean floor is covered by basalt. We have lots of these pillow basalts exposed here in the coastal California area. So what happens as the eruption occurs, the lava is quenched by encountering the cold seawater, and then it makes these kind of bulbous structures called pillows, right? And so these pillows will always have a round top, and they'll have these kind of keels that point down to the bottom, right? So here we some bunch of pillow lavas in here, again indicating that we have a subaqueous eruption there. And so now what's going on with the andesitic and rhyolite flow? So they're going to be a little bit higher in silica content, greater viscosity, right? They're going to have more of that silica polymerization, right? More silica polymerization. And then andesite flows forms large mounds above the vent, produces lumpy flows with bulbous snout, right? Travel only a few kilometers from the vent. Whereas blocky lava viscosity causes front lava to break into angular blocks, right? So it's kind of a more, it's not, you won't see hoi hoi lava in here. It's almost like the lava here, but it's going to be this andesitic structure. And then in terms of the rhyolitic lavas, these are going to be the lowest temperatures. Remember, because these are felsic, and felsic magmas are going to be low temperature. They're going to be the most viscous. They tend to accumulate right above the vent. In fact, sometimes we call these lava domes or plug domes because they tend to plug up the volcanic vent. And also, they're making short lava flows. They can make these lava flows called coulees, and later on I talk about the coulees here. And they don't flow very far, 1 to 2 kilometers at the most from the vent. And again, they have these blocky lava surfaces. Kind of going back to the andesite flows over here. Remember, I said that these andesite flows are going maybe 5 to 7 kilometers from vent. So they're moving a little bit farther than the andesitic flows, if the andesitic ones, than the rhyolitic ones, if the rhyolitic ones flow at all, right? So as we go along here, other deposits that we talk about are these volcaniclastic deposits. So again, somehow related to volcanic material, but it's broken, right? Remember, clastic is Greek for broken. And so your book talks about this famous eruption that occurred in 1943. There was a series of earthquakes in this region in Mexico, and then one day, finally, this crater opened up while the farmer was out there beginning to farm his cornfield, and it spewed out a bunch of sulfur gases, and obviously the guy ran and frightened from this event, and literally within 1 day, this vent built up to a small cinder cone that was 40 meters high, right? And then by a year, the cinder cone got up to 330 meters high, right? And then it lasted for about 9 years, right? And that's what happens to these little cinder cone volcanoes, is that they're kind of short-lived. In fact, we'll look at the Google Earth here. We're going to look at Paricutin here, and note that in Mexico, the tectonic setting here is that we have this trench here called the Middle America Trench, where this Cocos Plate is subducting under North America, under Mexico here. And along this trench, we're going to see a series of volcanoes. So you can see all these volcanoes in here. Some of the big ones are in Mexico City. There's a big Pico Orizaba above Veracruz here. This peak is over 18,000 feet elevation. Then there's the 2 peaks over Mexico City. And then there's Nevada de Ruiz and Colima. So we're going to go to this area here where Paricutin is. Oh, actually, Paricutin's over here. In fact, you could start seeing it right there. And one of the things you'll notice right away in the Google Earth image is the fact that there's very little vegetation on this region means it's a young volcanic event. Obviously, this volcano here is a larger volcano, but it hasn't been as active. Recently, it's a dormant volcano. But the one that was more recently active is this region here of Paricutin. And if we kind of zoom in, we'll see that it is a conical shaped cinder cone, right? With these lava flows, right? And let's see if we can kind of tilt this here. The volcanic vent right there, right? So, and you can see, if we kind of zoom in on this flow here, let's see if we can zoom in a little bit. You can see these structures here. So that's almost, on a larger scale, that's almost like those Pahoi Hoi lavas. So just by seeing these lavas coming out some distance here, right? Coming out in this region here. And if I asked you, based on this lava being slightly more fluid, being able to flow some larger distances from this volcanic vent, what would you call this? It would be a felsic volcano or more of a mafic volcano? And so that would be a good question there. All right, so let's go back to a few more things to say about basaltic debris and these eruptions. So again, they contain fewer volatiles, but enough to make these pyroclasts, right? So the pyroclasts, think of those fire-broken little bits of magma or flying up into the air, and they're called lapilli cinders, right? And in a little bit, I'll talk about the lapilli size rating here. It's between 2 millimeters and 64 millimeters. So but between sand size and about maybe 3 inches in diameter. And then as we go along here, I want to say a little bit more about volcanic gases. So we want to say that all magmas contain dissolved gas. So water, carbon dioxide, sulfur dioxide, hydrogen sulfide, methane, CH4 is methane, NH4 is ammonia, right? And one thing that we should make a point is that deeper in the magma chamber, the gas is dissolved, right? It's dissolved, so just like it's dissolved in a soda bottle. As soon as you uncork or open that soda bottle, the gas expands, right? It expands, and it's going to start forcing magma up toward the surface, right? So the gas is dissolved in the magma. Close to the top of the magma chamber, where there's less pressure, the gas begins to exsolve. So I want you to know this word, exsolve. E-X-S-O, and that means to separate, to separate. So the gas exsolves, right? Separates. So the gas separates from the magma, right? And now that gas expansion, right, it leads to this gas expansion, which is going to force magma through the volcanic vent. It really follows Boyle's law, right? Pressure at the same temperature, pressure and volume, right? So in the magma chamber, there's higher pressure but a smaller volume, right? But as the gas expands, right, we're going to see a larger volume. So because now it's coming up through the vent and exploding, the gas is going to expand to fill that volume, right? So one of the properties of gases will expand to fill whatever volume is available. Okay, so continuing with basaltic debris and basaltic eruptions. So we talked about these cinder cones a little bit. There's also shield volcanoes. And then there's flood basalt provinces. Later on in another video, I talk about cinder cones and shield volcanoes. Remember, these contain fewer volatiles, but enough to make those power class lapillis. And so we'll come back to these others in a moment here. But let's look at the cinder cones, right? So your book calls these scoria cones up here. And remember, scoria is a vesicular volcanic rock, and that's what these things are. They're full of gases that are sputtering out of the volcano. So imagine the gas expansion, gas starts to exsolve up down here, right? The gas starts to exsolve, forcing the magma up through the vent, and it's flying through the air, right? Flying through the air, bringing those pyroclasts or cinders onto the ground. And this type of fountaining is called a strombolian eruption. In fact, if we go, so here's a good example of a strombolian eruption here, where it's sending out these blocks and bombs, and in fact, we'll talk about these here in a moment here. So coming back to our document camera, we see that these can go a few hundred meters up into, or about 100 meters up into the air, right? So these pyroclasts. But the key thing is, out of the top vent, only tephra comes out of here. Those lapilli cinders. The actual lava comes out this flank vent, and that flank vent is called a boca vent. So you'll never really see lava coming out of the top of the cinder cone. You'll see it coming out of the boca vent. So if we go back to Paricutin here, we can see that here only tephra comes out of this center vent. But note the lava is coming out these flank vents on the side over here, right? So there's probably one over here where it came out, one right in here. So these would be the boca vents right here. They occur along the flanks of the volcano. Right?